information at you. Cool. I'm going to shotgun a bunch of information at you and hope that some of it sticks. And I'll talk more about this, but the goal is to just get you to see some things that are, more advanced or different than what you've seen in your classes. And if they're sort of like rattling around in the back of your mind as you get into higher level classes or you apply for jobs and all of that, you'll start seeing them pop up and you'll be able to make connections and say, okay, I recognize that. It's not totally foreign. And it just makes the whole learning process a lot easier. So with that being said, the way I classify the things I'm going to talk about, the things I'm going to shotgun at you, is I call them soft skills. There is some fundamental stuff that we'll go over. We'll probably just cover some basic data structures, have a day where we just go through a list of a bunch of stuff. But in general, these are going to be things that I have never been taught in classes, but that through my personal projects and jobs that I've had, I have found these skills to be necessary and I've had to develop them. And again, just sort of showing them to you so that you've seen them before and that when it comes time for you to have to learn them, you will have an easier time doing that. Now, the unfortunate thing about that is that I can't really quantify their impact on my knowledge. It's a very sort of loose collection of mostly random things, but as a whole, knowing them has made me just a more efficient developer. That's what I mean when I say soft skills in this context. And I said they're a random collection. There is one sort of underlying theme to quite a few of them, which is understanding computer science at a low level. And you'll learn more about what I mean by low level, as we get into it. We're not going to talk about hardware or anything, nothing that crazy. But yeah, so I'll talk more of that when I go through the roadmap. So also I have designed these to be language and or field or career path agnostic. So whatever you want to do under computer science, most of these skills should apply to that. And I am probably not the best judge of that because most of what I do is game engine development, C++. But I have had jobs as a web developer and some other stuff. So I have a bit of a mixed perspective. But hopefully the goal of this is that, no matter what you do, these really are essentials. These will help you in any field. That being said, most or all of the examples I give, code examples, if I give any, I haven't quite decided yet, will be in C and C++. And the reason for that is not that those concepts only apply to C and C++. It's just that the sort of quasi low level of abstraction that those languages provide happens to be really convenient for explaining these low level concepts in depth. Okay, so that's sort of a brief overview. I'll start this week, I'm just going to define some common terms that you probably have heard of if you're new. So I went through all the people who have applied so far, and it seemed about equal parts freshman, sophomore, and junior, and then there were a couple grad students as well. So for most people, a lot of this will probably be a review. So sorry about that. I will try not to bore you. But really the point of this, just going to go through a list of things that I find myself saying quite a bit, so that everyone's on the same page. And if I talk about some topic before we've fully gone in depth on it, I'm not just confusing everyone completely. Okay, so the first thing, I guess I'll write these on the board. I think the Zoom can see me, but this isn't super important. So the first thing is IDE, very basic. This stands for Integrated Development Environment. This is just a text editor mixed with a compiler, and usually it has some autocomplete features and stuff as well. So for Java, common ones are Eclipse, IntelliJ, C++, I use Visual Studio. And so yeah, IDE/editor, whenever I say that, just the place where you write your code. Compile, this is actually one that I'm realizing is maybe a bit weird because a lot of people in the survey responded, they said I'm interested in web development and machine learning. All of that is done in JavaScript and Python. and those are not compiled languages. So just so everyone knows what that is, compile is when you take the text source code that you've written and the compiler of the program turns it into something that will actually run on your machine. Okay, so now we have like a first sort of advanced concept, pointers and references. I'll just write refs. So this, we will have, I think, 2 whole workshops about pointers and memory and all that. I think these tend to scare people because they are difficult to think about at first. But just know that if I say pointer or reference, I'll try and stick to pointer. If I say pointer anytime before we actually cover them, what I mean is like you have some object in memory somewhere that takes up, a certain amount of space. But say I just have all these memory cells. So this is probably not on the Zoom. Let me draw it up here and I'll erase it. So I have all this memory and I have this thing, and then a pointer is just some value. Let me write this off to the side. Some value that you store in like a variable X, and instead of actually storing the data that's there, it just stores the place in memory where that is. That's all it is. And it seems simple, but they can get tricky to deal with. But that's the whole point of going over them. So I'm going to attempt to demystify that, which I assume is the main reason a lot of people don't like C++, is because you actually have to worry about pointers and all that, where in Java, JavaScript, Python, you don't have to care. Oh, another side note is I said I'll try to stick the pointer. These are also sometimes called references, which is confusing, but it kind of makes sense, like the name reference. But I will try to stick to pointers because in C++, references are a different thing. And so I'm going to try and stick to pointers, but then that leads us to the next vocab word today, which is dereference, which confusingly applies only to pointers. And all that means is, I shouldn't have erased that, but if you have this thing in memory somewhere and you have a pointer to it called X, then X just stores, a number that says where this is in memory. If you want to actually get the value that's there, you have to dereference the pointer. So basically the computer just looks at the pointer, reads that address, goes to it, reads whatever is there, and then returns it to you. And in C and C++, this is written with the star operator. So if X is a pointer, star X will give you the value at that pointer. Okay. So we're going to continue talking about memory just a bit. I won't go too in depth on these because, again, we have a couple workshops on them. But I probably, again, will mention these before we actually talk about them. And this is the heap and the stack. And don't confuse these with the data structures, heap and stack, although they are related. This I'm talking about like areas of a computer's memory. So I'll start with the stack. And hopefully, I'm not sure, can I draw over here? Is that visible on Zoom or no? Here or? Oh, okay. Yeah. Okay, so the stack is like, the way I think of it is it's like the place where local variables are defined. So if I have my method main, and then I have like an int x equals 5, this will be stored on the stack. And the notation that is commonly used for the stack is this concept of stack frames, where each method has its own frame on the stack, which is really just sort of a part of memory that method owns. So in this case, this would be the stack frame for main, and then we'd have x equal to 5 as a local variable of that. And local variable, I'm saying that very loosely because I don't want to get into it, but that's a convenient way to think about it. And then just for a further example, if I were to from here call print f, just sort of print something out to the console, then that would be another stack frame on top of main, and it would have its own local variables. And then whenever that finishes, it prints something out and it returns. Then that frame is popped off the stack. So again, we'll cover all this in depth, but that's the stack. And then the other part of memory is the heap. And I should definitely actually not call that. free store. So I call it the heap because I started in Java and that's what it's referred to in Java. But what this is like a place in memory where you need to allocate some memory, but you don't know how much memory you need to allocate at compile time. So the compiler can't like figure out where to put that basically. Obviously, that's a very common operation. I mean, a trivial example I could give is like you take in some integer from the user and then create an array of that length, just something like that. So that array would have to be allocated on the free store because the stack is sort of generally thought of as like a fixed size thing where anything that's known, any variables, any memory that can be allocated at compile time, or not allocated at compile time, but the size of it is known at compile time, will be put on the stack. And then anything sort of dynamically sized, that's sort of the key word is dynamic, will go on the free store. And this is just sort of a nebulous area. And like with the stack, we had that sort of organized notation of each method has a stack frame. The heap, I just usually draw it as a blob, like it doesn't even matter. It's managed by the operating system typically. And yeah, so that's all I'll say about that. Okay. So I will go through some data structures here. I'm not sure how in depth I should go. So it's 7:20. I think I'll just give a brief overview. And then as more and more survey results come in, with the survey that I'll put up a link for at the end, I'll read those results and see sort of what people's comfort levels are with the various data structures. And we might just have a day where, like I said, we just go through a list of them and cover them more in depth. But for now, just in case I use any of these words and you don't know what they are, let's talk about them. So I'll have a separate area over here for data structures. Okay, so the first one that everyone I'm sure knows by now is the array. This is just a contiguous block of memory of a single type. So you can have an array of integers, array of floats, array of strings, but you can't mix types. But the key point is that the array is contiguous. It is a block of memory. So I guess I could draw memory again, whatever this is worth, where you have, just some stuff and then some more stuff, and you'll have your array data here. And it's all in one place. And because of that, because arrays are allocated as contiguous memory, they are what we call a random access data structure, which means that if you want to get to any element, you can do that in constant time. And what constant time means, we'll have a whole lecture on all of that. But essentially, it means for free. That if I want to get the 50 millionth element of an array, I can just go straight to that element because it's all allocated contiguously. It's basically just math with pointers to get to that. Whereas with some other data structures, if you want to get to the 50 millionth element, you have to start at the beginning and go all the way through. And one such data structure is the linked list, sometimes also just called list. And this is quite similar to the array in that it's a given type, so you can only have a list of ints, a list of floats, whatever. But it is not necessarily contiguous. It can be, but you just sort of assume that it's not. And because of that, because it's not contiguous, it's not random access. So typical notation for a list like this is you'll have some nodes, and each node will have like a variable in them. So say I have a list of ints, and then an arrow pointing to the next node in the list. So it is ordered just like an array, but these nodes are not guaranteed to be next to each other in memory. So if I have 50 million elements in there, and I want to get this last one, whatever's there, I have to start at 5 and go all the way through. I'm thinking now it will be a good idea to actually have a day where I sort of introduce time and space complexity, and then we actually talk about all of these data structures a bit more in depth and just cover some common operations on them and the accompanying costs. But that's a linked list. These two are pretty simple. I think most people know those. So next we have the queue. which is usually implemented as a linked list because it's more efficient. I had a professor my first semester who had us implement a queue as a stack. I was not really happy about that. But so a queue is, I will just describe it as a particular implementation of a linked list, where you have that same basic pattern of, connected blocks or nodes, but you can only add to or remove from, you can only add to the end of the list, and you can only remove from the front. So if I had like this, and then I say, okay, I want to remove one, that remove operation invariably will remove the first one. So it gets rid of 5. And then you say, okay, I want to add one more. This is off the screen, sorry. But you have to add it at the end, and then another remove 10, so on and so forth. And so a useful analogy is just like a line, like if you're in line getting lunch or something, whoever's there before you is going to get out of the line first, right? Because they were there first, and so they get processed first. And that turns out to be useful. Even though it's not complicated, it just has some very convenient functionality for certain algorithms. Next is the stack, which is related to the queue and also related to the hardware stack that I mentioned before. Oh, and also I should say, all of these are like single typed. So you can have a queue events, floats, stack events, floats, whatever. And the stack notation is actually basically the same as the hardware stack one, where I showed you where each method has a stack frame. Except here, we don't have any method names or anything, we just have values. So if I have a stack events, say 1, 2, 3, and then I want to remove one, I can only remove 3. And then if I want to add one more, say 4, I can only add it to the top. And similarly to the queue, this is a very simple thing. It's basically just a wrapper class around an array, and queue is a wrapper around a linked list. But that functionality just happens to be convenient for certain things. And I'll give you one more bit of notation or just vocab that is typically used with these. So queue is what's called a FIFO or FIFO data structure, which stands for first in, first out, which makes sense. If you get there first, you're leaving first. And stock is the opposite, where it is a LIFO, which means last in, first out, because you can only add to the top. The next time you remove, it's going to take something off the top. Okay, so now we have a couple like more advanced ones. Tree, and I say this is advanced because there are so many different implementations of tree, like it gets insane, but they're incredibly useful. But for the most part, when I say tree, I'll just be talking about like a binary tree, which is, I'll draw this somewhere. I guess I'll just erase these. Over here or down here. I don't know if they can see it though. Can you guys see if I write down here? Yeah. Okay. You can't? Okay. I'll erase this. So a tree is sort of similar, you like diagram it similarly to a queue, where each bit of data that you're storing is in a node. And then for the typical trees that I'll usually be talking about, just assume I mean a binary tree, which is one where each node in the tree, so say this is some node that stores 5, has between 0 and 2 children. So this is a valid binary tree, as is this. But if I add like another node here, that's something else. That's not a binary tree. But these are, again, it's like very simple functionality. Well, that's not true. Trees are not very simple functionality. It's a simple concept, but this sort of inherent hierarchical ordering of data, again, just happens to be very useful for certain things. Yeah, so I'll have a whole thing, probably one of the first 2 or 3 lectures, but we'll go into each of these more in depth, and I'll cover like common operations on them and common use cases for them as well, because like knowing what this is without knowing how to use it is pretty useless. But that's tree. Next up, we have the set. And this takes its name from the idea of like a mathematical set, which is to say it's a group of things that is not necessarily ordered. And the key, like defining idea is that you can't have any duplicates in it. And I won't even draw that. That's super simple. But sets are, again, useful. Just that sort of simple functionality comes in handy in a lot of things, but also in the next data structure we're talking about, which is maps. So these, I use maps all the time. I think they are maybe the most useful. A map is a way to associate one piece of data of a given type with another piece of data of a perhaps different type or the same type, it doesn't matter. And maps are actually built on sets. So one of the things about maps is that you have this sort of set of pairs of objects. So say I have a map that maps strings to integers. So this can just be like, I have the string 1, and that maps to 1. And then, I could have 2, so on. And in order to, if I want to get the piece of data that is associated with the string 1 from this map, I will give the map this string and say, okay, find me the thing that's associated with that, and it'll return 1, assuming it exists. But here's where the set part comes in, is if I try to add something to 1, say I try to replace this value with something different, like 10, then because this is a set of pairs, these two can't exist together. So whatever's in there will just get replaced with that, with my new value. And then whenever I try and get the value stored at 1 or associated with 1, again, it'll return 10. And there are several different types of, well, 2 main different types of sets and maps. In C++, these are referred to as ordered and unordered maps. The ordered ones are typically just called a map or a set, and the other ones are unordered map and unordered set. In Java, this would be like you have tree set, hash set. Tree is the ordered one, hash is the unordered one. And they have different time complexities for their operations and stuff. But we'll talk about that later. Okay. Oh, and one last just thing. If you're like new to all this, just going back to like the basic terminology, function and method, I think are technically different things. I think function is like a global procedure, and then a method is like something that's part of a class. I use them interchangeably, and everyone I've ever met does as well. So if I say either one of those, I just mean a function and or method, just some block of code that you can run over and over again. Okay. So that's all the basic vocab I had. Hopefully I didn't bore you to death if you already knew all this, and hopefully I didn't go way too fast if you didn't know. But again, most of this or all of this we will actually talk about fully at some point in the future. Okay, so I'll talk a bit about the roadmap now. And this is tentative. This will certainly change as I sort of read all of the survey results and more of those come in. Just seeing what people are interested in, what they know and don't know. I'll probably change the order of these or add some new ones here and there. But as of now, and I don't think this one's going to change, but next week when we meet, we'll be talking about numbers and math. And that's a pretty broad category of things. But really what I mean is how numbers are stored in the computer. And you almost certainly had to do some of this in your like entry-level CS classes for integers and stuff. But we're going to talk, just review that so everyone's on the same page. We're going to talk about the different types of integers. And then the cool part is we're actually going to talk about floating points. So how you store, a theoretically infinite range of values in 32 bits or 64 bits. And this is one of those things particularly that like the knowledge of this is not really applicable to any one thing, but just knowing it helps you in different ways. Like when you need to know this, knowing it helps. But that'll be a pretty easy one. There's not too much heavy material there. Then we're going to take 2 lectures and talk a bit about strings and string operations. So we'll start with printf. And this may be something that a lot of people know, because I just sort of found out like a week ago that I think the first 1 or 2 CS classes here are taught in C++, so printf is more common. I sort of wrote this and planned this out, assuming that the first class was in Java. I don't know why I assumed that. But either way, we'll talk about printf. It's just like a classic way to format some output like dynamically at runtime and then print it to the console. And it's not just in C and C++. It exists in Java. They just ripped it out. Okay, so that's like part 1 of strings. And then the second part we're going to talk about is regex, which is the abbreviation for regular expressions, which I believe is actually like a very complex set of things, like mathematically. I don't know, all that's above me. But in terms of string operations, a regular expression is basically just a pattern that you can check a string against to see if it matches. And this is actually very useful. I actually use this quite a bit, just for like processing data. Like if I have a whole bunch of data and I need to reformat it for whatever reason, you can just like go to Chrome, open up the little developer console, and then use regular expressions in JavaScript and arrays and all that to just blaze through it super fast. So these 2 in particular are very, very helpful in terms of debugging, mainly for printf, and regular expressions for all sorts of things. So those are in general very useful. Next, we have 2 that we will be talking about memory stuff. So the first is just straight up memory. So this is where I will be actually explaining to you all the stuff about stack and heap and all of that, and the differences between terminology between Java and C++. That's all I really know about. I think anyways, like in Python and JavaScript, these concepts don't really exist, so it doesn't matter as much. But so we'll talk about the general layout of memory, and then pointers and references. And again, all the examples here will be given in C and C++, but these 2 in particular, I will make a strong effort to compare them to Java, because C++ is in a way like the parent of Java. So a lot of the syntax that you see in Java is reminiscent of C++, and I think that's interesting and valuable to them. But these are very important. Like, you know all the data structures, you know everything. If you know printf already, if you have some regular expressions, like come to these. These are, I think, by far, back to what I was saying about the common theme being understanding this stuff at a low level. Like this has helped me the most. Even in higher level languages, I've done a significant amount of work in Java and JavaScript where you don't need to know about these, but you can just go faster. You can identify bugs quicker. You can fix stuff. These are very, very important. Next, we'll just take sort of a detour, or end up here, and talk about templates in C++. This is also called generics in Java. And they're quite different actually between C++ and Java, and I will definitely touch on those differences. But they're also just sort of straight up necessary. Like they're not that complicated. I mean, the stuff in C++, as is a common theme, can get very complicated if you want it to. But mostly I'm just trying to introduce you to this stuff so that you can look it up later, because for most use cases, it's very simple, but extremely useful again. Okay, and then we will have just 2 lectures on like demystifying some commonly some topics that are commonly thought of as very difficult and confusing, because they are. But this is like the one area where I can actually like give you like some life hacks for like reading code and writing code a certain way, so that these things become more clear. First one is recursion, which, like pointers, I think tends to scare a lot of people. And the second is complexity. So this, we'll talk about space complexity, time complexity. Those sound like super fancy terms. All it means is like space complexity is how much memory does my program use, and time complexity is how fast is it. And that will sort of parlay us into the next section, where we will do some data structure design and some algorithm design. So I'm not sure which order we'll do those in. It'll probably just naturally just sort of be a mishmash of both at the same time. And these are more advanced topics. And this is like the point where I can't really help you that much. Like getting good at these things, not that I'm good, but I'm sort of experienced with these two things. You just have to do it. But hopefully I can show you something about my process for how I go about it. And we'll take a look at some like case studies of some data structures and some algorithms that I actually designed for the game engine series I did over the summer. But in general, just like everything else, I will try to make it applicable to whatever field you're interested in. Okay, then our second to last one, we will have probably a couple lectures, talks, whatever, meetings on debugging. And this is where this stuff really comes in handy. These two, I mean all of it, like memory pointers, printf is good for debugging. Templates are insanely good for debugging in C++. So we'll talk about some common ways, like to basically avoid writing bugs. Because again, just like the design stuff, like I can't really tell you how to be good at debugging. You just have to get experience with it. But what I can do is give you some things that I've learned about how to write code so that any bugs that you do write are caught more easily, essentially. So we'll probably have one or two talks about that. And then the very last topic, if we get to, because again, all of this is going to be shuffled around and we might have to skip some weeks and stuff for exams. But abstraction. So this is more of a software engineering type topic. I'm going to talk about how to structure your code in a good way, basically, because all of these things, while very useful, inevitably they fall into the trap that like every class that you'll take, every video that you'll watch, they'll fall into that same trap of, okay, I have this, how do I scale it up to like an actual application? If I'm writing code, if I have several thousand lines of code, you know, that I'm maintaining, or I have several millions of lines of code at whatever job I'm working at, that I have to figure out how it works and all that, and, you know, properly integrate with it. How do I do that? Like these give you the fundamentals, but doing it properly is a whole nother beast. And that is something that it's definitely more of an art than a science. There's no right answer to how to structure your code. But again, I will just go through some of the things that have helped me, and we might be able to take a look at some like case studies of my own code there as well. Okay, so that's the tentative roadmap. Oh yeah, and I forgot that I'm now just today figured out while I was up here that we should do one on data structures. Just running through all the basic things that I did in like 10 minutes there in more detail. And this will probably be, I think I'll actually put it here. Yeah, that's actually perfect. If I do it after all that easy stuff, memory, very, very relevant to data structures, and then templates and generic to help you sort of expand your knowledge of data structures. So that's where we'll put it for now. But yeah, that's the roadmap. Okay, so I have 20 minutes left. So I think, oh, and by the way, I didn't say this at the start, I meant to though. If you have like any questions or anything about anything I'm saying, like just raise your hand, that works, or you can just yell at me and whatever, like totally just interrupt, it's fine. But yeah, so I think there will be some time just for questions at the end of today, because we're not really doing a lot. But I have two more things to talk about. The first one is why this is important to me. I sort of mentioned at the start that like I love teaching, so I'll talk a bit about that and like what my drive here is, like why am I doing this? And then the more interesting one is why is this important to you? Like why is it good for you to be here, you know, in your free time, basically. Okay, so I'll start with myself. So in high school, I had a teacher called Dr. Strong, and he was my math and physics teacher for a couple years. And he, whenever he was like writing stuff down on the whiteboard, because it was all math and physics, is a very graphical topic. So he was always up at the whiteboard, and he would say, okay, I thought of something. This is a pencils down moment. That was his word for like, I'm going to talk about something that's like a tangent to this, and it's not going to be on the test, but it'll be interesting if you listen. And I always loved that. I thought that is such an excellent way of teaching, because it's sort of, rather than just a lecture where you sort of like blaze through the whole thing all at once and don't give anyone any breaks, sort of what I'm doing right now. It sort of gives everyone a chance to like recenter and take a break if they're writing notes. And the people who you lost along the way, they can sort of become interested in this new thing that's not going to be on the test, but it's probably pretty cool. And those pencils down moments like were so valuable to me that I'm still realizing the wisdom that this man had to share. It like, and again, this is sort of a thing like the CS soft skills, like my definition of soft skills. I can't really quantify it in any way. It's just that having been exposed to all of this additional stuff that we didn't really need to know, still helps me out to this day. Like I'm in a linear algebra class right now, and Dr. Strong was a teacher who taught us some linear algebra, and stuff that he said back then, I am actually applying to my college course right now, which is really, really cool. So yeah, pencils down. And he, again, like he never really went in depth on this. It was sort of what this is going to be, just a shotgun of a bunch of stuff at you, hoping that some of it sticks in the back of your mind and you can realize the importance of it and what he actually meant at a later date. I'll give one particular example of this because it's like, so I remember it so vividly in my mind. It was when we were learning linear algebra, and this was just very basic stuff. It was like, here's how you do operations on matrices. Here's how you multiply matrices. Nothing crazy. But he said, okay, so like we're done doing this example multiplying matrix. He said, okay, this is a pencils down moment. So there's this thing called a fast Fourier transform. And I still don't know what that is. I can guarantee you that like if I took any sort of engineering classes here, I would find out pretty quickly. But I can further guarantee that if I eventually do find out, I will think of that moment and I will understand, okay, this thing, which is just sort of this incredibly nebulous, complex operation to do something to decompose a function into its component waves or something like that, it has to do with linear algebra. And like immediately there, I have a knowledge base that makes this stuff less foreign and just gives me an additional thing to Google about it. Basically, I have more of a grounding and you just feel less lost. And so really, my goal is for all of these lectures to be just one like long pencils down. It's stuff that you don't need to know for your tests in class, but really it is very useful and it will help you not only in class, but also in programming on your own projects and any jobs you get and stuff. Like understanding all of this stuff is incredibly valuable. So the last sort of thing about why this is important to me is back to Dr. Strong for a minute. He like made me enjoy math. Like at that point, I had already started programming and I was very into that, but I was terrible at math. I was just not interested in it. I didn't get a lot of it, but he really gave me stuff to be interested in. And the way he did that sort of inadvertently was through these pencils down. So it wasn't anything targeted at me, but I just realized that a lot of the things he said during those, I could actually apply to game design, like the game engine projects that I was working on at the time, this basic math, I needed to know it. And hopefully I can do the same to you, where even if you're interested in web development or machine learning, Python, JavaScript, these higher level languages, hopefully this stuff that you don't need to know, I can get you interested in it. And so you have seen it before, and maybe you become interested in yourself. Okay, so last up is why is this important to you? So the main point is that knowing all this stuff will just give you different ways to look at problems. And straight up, like attacking a problem from different angles will give you a better solution. It'll make it easier and it'll be faster. Like that's just how it works. So all this stuff, and I'll talk about like the different kinds of problems. Like, what do I mean when I say attacking a problem? But yeah, so this stuff will help you really solve it, but I'll get into that. Okay. So another reason this is important to you is that my dad right now is switching careers, and he's doing one of those like web development boot camp things where you like pay to do a class for like, I don't know, 8 or 9 months, and at the end you get some certificate or something like that. And he said that the most valuable thing he's gotten out of that is not all the knowledge of like how to do web development, which he didn't know. Like he'd never done any programming in his life up to that point. That wasn't valuable because he realizes like, okay, all this stuff, like just figuring out the syntax and like the basic structure of programs, like I can just look that up. He said the thing that's important is the confidence he's gained from being forced to solve problems. And that being forced, I mean, not literally, but he sort of paid for it. And so that's the whole idea, is you pay for this thing so you don't want to quit. And I guess that's sort of what's happening with college. But I think that in a strange way applies to what I'm doing, like that confidence. Like, why should I be able to be up here talking to you? Like, a lot of you are older than me, far smarter than me, way more experienced. And so why should I be up here preaching to you about all the basic experience I've gained and why it's important? Well, it's confidence. It's confidence in my knowledge of the knowledge I've gained, and I think that's valuable to share. But also the knowledge of my knowledge. I know what I know, and I know that it's valuable, obviously, because I've used it. But I also know what I don't know, I guess. And that's the key point, is that all of these tricks, like I want you to be able to walk away from all of this thinking like, okay, here's a problem. I have no idea where to start, but I know I can solve it. And that's not the same thing as arrogance. Like, you shouldn't just say, oh yeah, I could do that, and then don't even try, because that doesn't work. But you should be confident that you can learn to solve any problem. And learning more complicated things are inevitably based on more basic things. And so these are the basic things that have helped me solve problems, learn to solve problems. I believe will help you learn to solve problems as well. So let's go back to what I was saying about like the different kinds of problems. I'm doing quotes a lot. So there's two ones that I think are particularly relevant. There's school problems, like I have this test, and then there are other problems, like I'm writing this program and very vaguely, it's not working. What's not working? Is it not compiling? Is there, something going wrong? And it is like, when I say that, I should further clarify, I'm talking about personal projects where it is just you, or maybe you and a couple of your peers working on some code, not for a class, just for something as a learning exercise, or just out of interest thing. And those are the very hard problems. Like the problem of I have a test and I don't know anything, you can study. Like your professor is there. He gives you homework to force you to learn these things. You have a textbook likely that you can just read, and you can pass the test. But when you're in an environment where you don't even have access to that kind of guidance, it is incredibly hard to solve those problems. And what I found, as sort of, I consider myself like a self-taught programmer for the most part. What I found is that that initial step of like difficulty of not having access to any guidance and not really being sure of what's going wrong, is just as hard as actually solving the problem once you find it. And furthermore, for your specific case, like there might not be a solution. You may have written your code in such a way that whatever constraints you now have cannot be satisfied. And you need to be able to identify that. And I would just like to reiterate this, not only because it's something that I think I have significant experience with, but also just to reinforce the idea that I can't really like teach you how to do this stuff. You just have to do it. It is very hard. Solving problems on your own is very hard. Like being in an environment, an academic environment even, I feel, detracts from like my confidence that focusing on personal projects instead of school or relationships or whatever else, it detracts from my confidence that that's like a smart move, you know, because everyone else around me, not everyone, but most people around me are worried about doing well in school, which is good. That's a fine endeavor. You know, that's a very productive mindset. But it's not something you can learn, but it is something that I can teach you how to learn. I think that's really what I'm trying to get at. But because of this difficulty of solving problems in an environment where it's just you working on the code, and you know these are problems that you have created yourself, because of that apparent challenge, I just sort of, well, that and like meeting people, most of the people I've talked to, I just assume that most people, most CS students, just avoid self-driven projects altogether. And this is something that can work, I assume. I mean, if you have, you know, a crazy like 4.0 GPA or whatever, and you can get internships through that, then sure, that's like your gateway to a career, right? But I prefer to learn by doing, I guess, and I'm not saying that that is like a more correct way to learn. I'm not saying that school is not valuable or anything like that. But I do think that no matter how you learn, actually doing self-driven projects will just increase your knowledge in general. And that can have real benefits in school and in your career as well. Like just a personal example here is I have a friend from high school who did competition programming with me. And she was always a way better student than me. She had a crazy high GPA. She was in all these clubs. She ended up going to the Turing CS program at UT. And I didn't even get accepted to the UT CS program, let alone Turing. But at the end of our senior year, we both interviewed for the same job with the same guy, and I got the job because I had programmed and I was able to like pass the technical interview part of it. And she wasn't, not because she wasn't smart, but just because she focused on different things. And obviously that experience has given me a very strong bias where I say, okay, if you want a job, like you need to do stuff on your own. Of course, there are always exceptions, but I think regardless of, you know, your mode of learning and and looking for jobs and stuff, this like doing stuff on your own is very valuable. And that's I think I've said this several times now, but that is the point of all this, is for you to be able to walk away and have some basic knowledge about not how to do your own projects. I mean, some of this is directly applicable to that, as we'll see, but how to learn to do your own projects and like drive your own learning. And one last point I will say is that there is a connection between doing your own stuff and performing well in school. They're not entirely different. I'm not saying only work on your own projects, just put those on your resume, don't care about your grades, nothing like that. But there is this thing that sounds ridiculous to say, like it sounds incredibly idealized, but doing projects on your own, you might find things that you're like, oh, hey, I can apply that to this class. And like, okay, I have this project now that everyone else is struggling with. I wrote something just like that a week ago for my own thing. I can just copy and paste it and turn it in 5 minutes. And again, that sounds incredibly idealized, but for me at least, it is actually true. Like I constantly find things in my classes assignments where I'm like, oh yeah, I know that. Like I've just done it. Like it's fine. I already learned that, not like intentionally necessarily, but just as a byproduct of working on something else that I find interesting. And a bit further to that point, you can often establish like a cycle in your learning between what you work on your own and what you learn in your classes. Like I think I'm doing that right now with my linear algebra class. You know, I say I'm into game engine development and all of that, but really I have not done any type of 3D graphics, any type of 3D anything, which, you know, if I want to get a job in that industry, I think I probably should start working on that. But all of that is linear algebra. And so I'm like, okay, I have an external motivation for doing well in this class, and I can sort of feed off of these things where what I learn in linear algebra, I can apply to my personal projects, and then I will inevitably learn some new things there that then, you know, will help me pass a test or whatever. And again, I'd just like to say, this really, like, it actually does work like that. It sounds stupid, it sounds ideal. That's how it works. And so I think, again, regardless of how you learn, regardless of what your goal is, if you're not working on personal projects, you should start working. And that's the point of this. Okay, so that's all the content I had prepared for today. I guess, are there any questions or whatever? You can ask them out loud, or you can come up to me afterwards. That's really fine. Yeah. Oh, good point. Oh, and I forgot to show this as well. You're supposed to scan that. That's my bad. I was supposed to show that at the start. But this just like, I don't know, it's something for ACM to track attendance or something. So I'll leave that up for a couple minutes. I am. Yeah. What's your name? Okay, I talked with you. Awesome. Yeah. Very nice to meet you.